So in the earlier slides, we had discussed about the overall detailed overview about the CVD process. So this CVD process is widely used as a thin film deposition technique in which gaseous precursors react or decompose on a heated substrate to form a solid material. So ideally, as discussed earlier, this heated substrate act as a catalyst for the growth of these thin film, and CVD is crucial for producing high quality films in semiconductor manufacturing, especially in the case of nanotechnology, protective coatings. In particular, if you look into the advantage of the CVD process, the CVD process will ensure a uniformity in the thin film, and it also results in a high purity deposition. So that is one advantage of this CVD process. So if we try to see the closer view of the CVD process, so there is a kind of a vacuum chamber which exists, and we have a heating zone which basically helps in catalyzing the growth or the film deposition, and a precursor flow over there, and there is an exhaust which tries to come out of it. So as far as in this precursor gas introduction is concerned, so we have the reactive gases which are considered as precursors are introduced into the reaction chamber, and in the case of gas phase reaction, the precursor gas undergoes a thermal decomposition or chemical reaction near the heated substrate. As far as film deposition is concerned, the resulting solid material form a thin film on the substrate. Byproduct removal, the unused gases and the reaction byproducts are removed using a vacuum system or a gas flow rate. So as mentioned earlier, so we will be using an appropriate catalyst for the growth of this CVD process. These CVD process are classified based on the type of functionality as well as based on the type of application. The first type of CVD is called as atmospheric pressure CVD. So the main function of this atmospheric pressure CVD is it is conducted at an atmospheric pressure using a controlled gas flow rate over a heated substrate. So the main advantage of this particular process is it has a high deposition rate, and with reference to methodology perspective point of view, it's a kind of a simple step process. In the case of disadvantage is concerned, it has a poor step coverage, and sometimes it may lead to a non-uniformity based systems. On an application perspective point of view, any kind of oxide coating or protective layers in microelectronics are well taken care using this atmospheric pressure CVD. Next, we have a plasma enhanced chemical vapor deposition process. In the case of plasma enhanced chemical vapor deposition process, it uses a plasma which is nothing but an ionized gas to enhance the precursor deposition and allowing deposition at a lower temperature. So the main advantage is the lower deposition temperature, good film quality, and it has an enhanced control over the film properties. However, the major disadvantages which is observed in this particular system is it is a more complex systems, and it requires a high amount of plasma needs to be generated in them. When with reference to application perspective point of view, it can be used as a passive layer, it has an optical coating, and it is mainly meant for MEMS based devices. Now we have the low pressure CVD process. As far as the low pressure CVD process, as the name suggests that these low pressure CVD process are performed under reduced pressure, that is around 0.1 to 1 torr, to improve the film uniformity. And as far as advantages perspective point of view, it has a high quality film, and it has a better step coverage and a reduced gas phase reaction. Whereas disadvantages perspective point of view, it has a slower deposition rate as compared to the atmospheric pressure CVD. And application perspective point of view, basically these kind of systems can be deployed for silicon nitride, polysilicon, silicon dioxide deposition in the case of a semiconductor fabrication. Now, in the case of metal organic CVDs, which we call it as MOCVD, these are used for metal organic precursors to deposit complex compounds, often at a high temperatures. And the major advantage is it can deposit 3 to 5 and 2 to 6 semiconductor materials, range of 2 to 6 semiconductor materials. The major disadvantages is the precursors are highly expensive, and it is highly sensitive to the process conditions. When we try to talk about applications, so the material like gallium nitride, then indium peroxide and other compound semiconductors for LED, lasers and high frequencies are some of the key outcomes of this particular metal organic system. The most important, or I would say like a specialized CVD process is called as an atomic layer deposition. So, these atomic layer deposition involves sequential exposure of precursor in a self-limiting manner, allowing precise atomic scale film thickness control. So, the main advantage is it has an exceptional uniformity and a precise thickness control. The major disadvantage, if we try to look into it, is it has a very slow deposition rate at higher cost. Application perspective point of view, materials with high dielectric, high barrier layers in advanced semiconductor devices, etc., may be considered as a part of can be easily deposited using this atomic layer deposition. Now, if I try to make a overall comparison with reference to a physical vapor deposition process and a chemical vapor deposition process, like the deposition mechanism as we had discussed earlier, it is in the case of a physical vapor deposition, the physical material is getting transformed in the form of a vapor and it is used for a deposition. In the case of a chemical vapor deposition, chemical reaction of a precursor gas is used on the substrate. And process environment perspective point of view, it is a kind of a high vacuum and a plasma assisted system, whereas in the case of CVD perspective point of view, it is a atmospheric low pressure or plasma enhanced perspective or a plasma enhanced. Now, with reference to temperature requirement is concerned, these PVD are capable enough in such a way that it can work in the range of 100 to 500 degrees Celsius. However, CVD perspective point of view, it has a higher range in the range of 300 to 1100 degrees Celsius, except in the case of PVCVD and ALD. When we try to compare the film purity, which is nothing but the active layer purity, it is highly pure in the case of PVD process. May contain, in the case of CVD process, this may contain certain amount of impurities from the precursor gases. When we try to talk about the step coverage, it has a limited and non-conformal, whereas in the case of a CVD process, it has an excellent conformal coverage, which is considered to be one of the major advantage of this particular systems. Now, with reference to deposition rate perspective point of view, these are generally slower. However, as far as in the case of CVD process is concerned, the CVD process are much faster compared to the PVD process. Now, with reference to material range is concerned, we have metals, oxides and nitrates which are exhibits over here. However, on the other hand, in the case of CVD, we have metals, semiconductors, ceramics and polymers which exhibits. Film density perspective point of view, it is high but may have voids in some methods. However, in the case of CVD perspective point of view, it is high, dense and uniform. Adhesion to the substrate is concerned, it is good but requires a kind of a ion bombardment for better adhesion. That is, you need to have a kind of a surface treatment to have a better adhesion property. So, this surface treatment might be either a kind of creating a kind of roughening the surface to have a higher adhesion, or we can also heat the substrate to have a higher adhesion. However, with reference to CVD perspective point of view, we have a high, dense and a uniform film which exhibits in this particular process. Adhesion to the substrate is concerned, it is good, but it requires a kind of a ion bombardment. And the equipment complexity perspective point of view, it requires a vacuum and a plasma system, whereas in the case of a complexity perspective point of system, in the case of CVD process, it requires a gas handling part and a reactor and a vacuum system which exhibits over here. The process control perspective point of view, we have the physical parameters, and in the case of CVD perspective point of view, there is a kind of a chemical reaction which exhibits. So, automatically for a chemical reaction, we require certain amount of elements and sub-elements which needs to be integrated, which includes a gas flow, a reaction, kinetics. Some of the common techniques of this particular process of PVD are sputtering process, thermal evaporation process, electron beam process, PLD, which is nothing but the pulsed laser deposition process. However, in the case of CVD perspective point of view, we have APCVD and low pressure CVD, physically enhanced CVD, metal oxide CVD and ALD, which we had discussed in the earlier applications. Wherever we require a kind of a hard coating, or wherever we require a kind of an optical coating or a decorative coating and a semiconductor metallization, such kind of PVD system exhibits. However, in the case of a kind of a semiconductor fabrication or in kind of layers where we have a kind of a surface which exhibits, there we have a kind of a such kind of CVDs can be efficiently used. So, this will help us to identify our coating techniques or microfabrication techniques based on our requirement or based on the material what we are using it for a micro robotic application. Now, let us talk about this photolithography process. So, photolithography process is a kind of, like as we had discussed earlier, it comes under the classification of top down approach, where we have a deposited layer, and then whenever we want to remove that deposited layer, so we try to integrate a mask in this particular region, and then we try to expose to a laser or sometime with reference to chemical etching, so that appropriately we can remove the material based on our requirement. So, just to give you an overview about this photolithography, lithography means it is a combination of two Greek words, which is nothing but litho and graphene. So, which means litho means it's stone and graphene is to write. So, this term photolithography process involves the use of an optical image and a photosensitive film to produce a pattern on a substrate. So, it's a technique to create a pattern on a substrate with a sub-micrometer resolution. So, in microelectronics applications or micro robotics applications, these patterns are necessary to create certain amount of electronic layer on top of it. So, this is where exactly this photolithography plays a vital role. So, these photolithographies is used to set a pattern for mask for cavity etching in bulk micromachining or for thin film deposition and etching of sacrificial layer in the case of a surface micromachining. In all these domains, such kind of photolithographic process are being employed. Now, I will introduce you to two important terminology. Almost these two terminologies are well performed using the same process. One terminology which we call it as a etching, the other terminology which we call it as a patterning. So, what do you mean by an etching? Etching is nothing but a removal of a selective material, whereas patterning is something like creating a kind of structure based on our requirements. Okay. So, like in the case of etching process, wherever I have a material and if I want to remove a material, so this etching process can be efficiently used. However, in the case of a patterning, like I have a layer and I want to create a kind of a patterned structures on the surface, so that this will be helpful for me to functionalize my system based on my requirement or based on the characteristics. Okay. Let us see the conventional process that flows in the case of a photolithography process. In the case of a photolithography process, in order to introduce you to the photolithography process, let us consider a wafer over which an SiO2 coating is done. So, the main motto of this process is like I need to create a kind of a pattern structure over the surface. So, on this coated structure, so we are trying to use a photoresist layer, and when we try to introduce this photoresist layer, so the main function of this photoresist layer, it is something like this is the region at which exactly we may need to remove the material. Now, what we are trying to do is, so there is a kind of a masking which exhibits. So, this is a kind of mask which exhibits over here. So, in this mask, the main objective of this particular process is I need to create a kind of a structure something like this. So, in this structure, so it is a kind of a bonded structure where we have two masks and then we may need to remove the material. So, what we can do is, so we have a mask which is available and a UV light is made to interact on the material, and the UV light is made to pass through the photoresist, and this is exposed to the photoresist. If you closely observe in this mask, one layer of mask is kept blocked and the other layer will have a direct interaction on the photoresist, thus leading to the removal of the material over here, and the region which is masked is kept constant. So, this is the overall conventional process of a lithography which is being efficiently used or administered for difference. So, overall, if you try to look into the overall nomenclatures or the elements which are been participating in this etching or patterning. So, we have a wafers. So, wafers can be anything depending upon the application requirement. So, ideally wafers are nothing but the substrate which we have been which we have discussed a lot. Then we have a coating. Coating of the material is performed depending on the crystalline and as well as the amorphous requirement. So, what we try to do is, so we have a coating layer and then we try to use a kind of a certain amount of treatment to create a crystalline structures or a single crystal structure, etc. A photoresist which is available, the main function of this photoresist is it acts as a light sensitive material that allow for a precise creation of the patterned coating on the surface. Now, we have a mask in place. The main function of this mask is it acts as a template for the circuit pattern on the chip. And when we try to talk about the developer solution, this developer solution is used to dissolve the unexposed matter to eliminate out and form a specific pattern as and when required. So, these are the different elements which are available. So, when I try to closely observe the functionality of a photoresist, the photoresist is a kind of a light sensitive material which is used in photolithography to transfer the pattern onto a substrate. So, if I try to classify this photoresist, so we have a positive photoresist and the negative photoresist. So, in the case of a positive photoresist, the exposed region dissolve in the developer, leading to the unexposed area of intact. In the case of a negative photoresist, the exposed region become cross-linked and remain when the unexposed regions are dissolved. So, if you try to look into the different composition of the photoresist, the different compositions of the photoresist includes a polymer, which is based on the material which providing the structural integrity. The photoactive compound, which we call it as PAC, which enables the light sensitivity. There is a solvent which is available. The main function of the solvent is to control the viscosity for spin coating or any other kind of coating based on the requirements or based on the characteristics. Now, if we try to look into the overall development process, the development process involves it uses an aqueous or a solvent based developer to remove the selected region based on the exposure type. However, with reference to key properties are concerned, it has a high resolution and contrast. Chemical and thermals, it has a good chemical and thermal stability. It should have a good adhesion to the substrate and it should be a kind of a resistance to the etching process. Now, the common photoresist materials which exhibits are, in the case of positive, there is a AZ series material which is available, or a Shipley 31S1813 is a material which is available. In the case of a negative photoresist, we use a S8, NR9 and KMPR which are used as a negative photoresist material. Now, let us discuss about masking in a photolithography. A mask in a photolithography is a transparent plate. Typically, it is a quartz or glass with opaque pattern that define the circuit layout for microfabrication. So, the common material included in the quartz, common material which is included are kind of a quartz, sometime it might be a kind of a soda lime glass or it might be a fused silica with chrome layer for patterning. There are different types of masks are there. One we call it as a binary mask. So, the main function of the binary mask is it opaque region, it blocks the light and a transparent region allows the light to transmission. So, it is something like this. For example, if I need to create a mask and if I want to create a pattern, this is a kind of a binary pattern I can exhibit, and when I try to expose it, the light falls on it, finally it ends up in a textured pattern, something like this. finally it ends up in a textured pattern, something like this. So, this is an application of a binary mask. We have there is other kind of mask which is there, which is called as a phase shift mask. This phase shift mask is used for enhancing the resolution by phase shifting the light to improve the contrast of it. Then there is a grayscale mask. The grayscale mask uses a 3D microstructure by allowing a different exposure intensities. When we try to look into the resolution role of it, it basically determines the feature size in the microfabrication, and it also affects the final device performance what we are looking for. Now, as far as in this particular patterning or masking is concerned, so we may need to understand certain terminologies. So, one terminology is related to fabrication, which is created using an electron beam lithography or a laser writing for high precision. So, when we try to talk about usages, it is placed between a UV light source and a photoresist coated wafer to transfer the pattern. On an alignment perspective point of view, it is critical for a multi-layer process to ensure an accurate feature of overlay. When we talk about mask defect, any imperfection can lead to a defective circuit pattern, or it may also reduce the yield. As far as cost consideration is concerned, it has a high resolution masks are expensive. It acts as an alternative solution which includes a kind of a maskless lithography for prototyping. Storage and maintenance, it requires a clean room to handle such kind of system. So, these are some of the things which we may need to consider. Now, when I talk about this photolithography and the photoresist developer, as we had mentioned earlier, it is classified into two. One is called as a positive photoresist developer and the other one is called as a negative photoresist developer. So, the positive photoresist developer is concerned, the exposed region of the photoresist becomes soluble and are removed by the developer. Most of the common developers, which includes a kind of a aqueous alkaline solution. So, this is a kind of a aqueous alkaline solution which is heavily used, and then sometimes sodium hydroxide or potassium hydroxide is also used in a diluted concentration to develop these positive photoresist developers. In the case of a negative photoresist developers, the explosive region becomes cross-linked and remain while the unexposed areas are dissolved. So, the common developers includes an organic solvent such as xylene or methylene or isobutylene ketone are heavily used as a kind of a negative photoresist developers. So, some of the key parameters which affects these developers are, one is a kind of a concentration, because concentration has an impact on the development rate as well as on the resolution. The time over the development can lead to an excessive material removal. Temperatures, the high temperatures may increase the development speed but can also cause unwanted diffusion in the system. Agitation, which may ensure the uniform development and the pattern accuracy. So, these are the key parameters which has to be considered with reference to patterning perspective point of view.